In this video, we're going to start our study of complex numbers. So we just finished chapter 7, where we're starting with chapter 8. Chapter 8 is on a few different topics, but mainly the first 4 sections, 4 out of the 6 sections, are all about complex numbers. Now, this probably isn't the first time that you've dealt with complex or imaginary numbers. There was an entire section on this topic in the algebra textbook, the algebra playlist. However, here in trigonometry, we're going to go into a lot more detail on complex numbers. So everything that we learned in algebra, we're going to cover again here in trigonometry, but we're going to go into a lot more than that. Okay, so let's get started. Here's the opening image for this chapter. It says, high-resolution computer graphics and complex numbers make it possible to produce the endless self-similarity property of a fractal image. Interesting. So these are fractals within this image. And there's a way to view fractals from the perspective of complex numbers. So we'll come back to this in the upcoming videos. Okay. So again, a lot of this stuff you're going to be familiar with from algebra. However, mixed in is going to be brand new information as well. Okay, the basic concepts of complex numbers. So there is no real number solution of the equation x squared is equal to -1. So before you ever heard about imaginary numbers or complex numbers, if you were given the equation x squared is equal to -1, you couldn't solve it. And why not? Because there's no real number when you square it, you get -1. That's the problem. Okay, so it's really helpful every time you think about real numbers. If you think in your head all real numbers, the set of all real numbers, you want to think about a line like this. Now it doesn't have to be a horizontal line. It can be any line, but you just want to think about a line. Okay, we know a line extends infinitely in both of its respective directions. Okay, and then at the middle of the line is 0. You label 0, and then you just make equally spaced tick marks. You just put a scale on this line. So this would be 1, 2, something like that. How you space it's all up to you. It doesn't matter. So here, this is linearly scaled. So like the specific physical distances on your computer screen or on your paper, like if you measured off 5 millimeters, that means that at any position on the scale, you're adding the same amount or subtracting the same amount when you go 5 millimeters on the scale. That's a linear scale. But there's also logarithmic scales. You could make this a logarithmic scale. It doesn't matter. But the idea is you can think about the entire set of all real numbers as existing on a line like this. This contains all integers, rational numbers, irrational numbers, everything. This contains all negative numbers, right? So when it comes to understanding imaginary numbers and complex numbers and really all of the possible numbers that exist in mathematics, it's helpful to think about real numbers as existing on a line like this. So this is the set of all real numbers. Okay, and so again, in order to solve this equation, you need to answer the question of what number, when squared, do you get -1? But the issue is there's no number on this infinitely long number line that you can plug in here and you get -1. That's the issue. Okay, so to extend the real number system, it says, or just the number system, right? The existing number system, to include solutions of equations like this, the number I is defined. So a new number is defined. Okay? Now you might say, well, why don't we do the same thing with dividing by 0? Why don't we say 5 divided by 0 is some new number? K. Well, I talk about this in detail in the algebra playlist video on dividing by 0. The problem with this is that this would conflict with the existing math, trying to define something, a meaning of dividing by 0. But they're able to, this isn't an issue with defining a new number I to represent the something that can solve this equation. Okay? So what is the number I? I is a number that is equal to, is defined to be equal to the square root of -1, or technically this would be the principal square root of -1, which is kind of confusing because you think about the principal root only returns the positive value, right? Like the principal root of 4 is 2, even though 2 squared is 4 and -2 squared is 4. Okay, but it's still the same idea in the sense that, so another way of looking at what I means is that I squared is equal to -1. Okay, because you square both sides, right? You get I squared is equal to -1. That's another way of looking at exactly what I is. I is a number that when you square it, you get -1. But like it says here, it says, note that minus I is also a square root of -1. So yeah, in the same way that 2 squared is equal to 4 and -2 squared is equal to 4, but this, the principal root of 4, is equal to just 2. Well, it's a similar idea in the sense that with I, in the sense that, okay, I squared is -1, but minus I squared is also going to be -1. Why? Because, okay, -1 squared is 1, so the negative goes away. What are you left with? I squared. But what is I squared? It's -1. Okay, however, the principal root, square root of -1, is just I, not plus or minus I or anything like that. That's the idea. Okay, so square roots of negative numbers were not incorporated into an integrated number system until the 16th century. And at that time, they were mostly used just as solutions to equations, like x squared is equal to -1. But today, complex numbers are used extensively in science and engineering. Okay, so before we take a look at what exactly they mean by a complex number, so like what's the difference between this number I here and what they're calling a complex number, one thing to note is that you can treat this number I like it's any other number. Okay, so we're going to operate with this just like we would do with any other real number in terms of distributing different just properties of multiplication, adding, subtracting, dividing, etc. Okay, so you treat this like a regular number. Now, there are some slight nuances that you need to be aware of in terms of how this number integrates with all of the existing ways that we know how to operate with real numbers. And I'll make sure to point those out as we go. But in general, you just work with this and treat this like you do any other real number, with just keeping in mind that what this is that this is, when you square this, it equals -1, or you could look at it like the principal root of -1 is equal to this. That's what this is. That's the number that this is. And this is typically referred to as an imaginary number. I is referred to as an imaginary number. But we'll see in a second what the more precise details of the notation is when it comes to imaginary and complex numbers. So what's a complex number? What are we talking about there? Okay, well, all a complex number is that, so okay, let's take a look here. If A and B are real numbers, then any number of the form A plus BI is a complex number. In the complex number A plus BI, A is the real part and B is the imaginary part. So, okay, they're saying that you have A plus BI. Okay, and A and B are real numbers, any real number, positive, negative, whatever, any real number. And then I is just I, it's just itself. Okay, so this is a complex number. That's it. So again, A can be any real number. Any real number. B can be any real number. And then taken as a whole, the sum of these two parts here is what's called a complex number. All right, so what is this? Well, what's the purpose of this? Well, you'll understand this more as we continue learning about complex numbers. But what you can think about is that, so yeah, when it comes to square roots or like needing to take a square root of both sides of an equation to solve it, well, yeah, in that case, maybe all we need is I. We don't need complex numbers. However, if you think about it, though, this issue, the same issue we had here, is going to come up if you've got like, x to the fourth is equal to a negative number. When you need to take any kind of an even root of a negative number, you have the same problem. Okay, and so with that, think about this. So we know that, so I squared is equal to -1. Okay, great. That's the whole point of this number I, that when you squared it, you get a negative number. And so ideally, it would be the case that if you take I to any even power, something negative comes out of it. Because again, it's not the idea of just squaring any real number, positive or negative, and you just get a positive output. It's any even power. Okay, so, all right, well, what would I to the fourth be? Ideally, this would just work itself out to where this comes out to be a negative number. Well, okay, well, that's I squared times I squared. That's I squared is -1. You get a positive number back. So just having I, or just I with a number out front, a coefficient out front, isn't going to work in and of itself when we try to work with even powers greater than 2. And so that's where the idea of complex numbers is going to come in. Okay? And, it's not just with square roots or the power of 2 or even powers or even roots. It's anywhere across all of the existing mathematics where this issue comes up, that you want to define this new number and how it's operated with to be able to solve all of those issues that are rooted in this fundamental issue that you kind of sum up here with the definition of the imaginary number. Okay, and so with that, when you think about imaginary numbers, this new system of numbers that go beyond just the real numbers, really what you're thinking about is complex numbers. And the reason why it's useful to think about real numbers along a line like this is because it makes it really intuitive to understand complex numbers whenever you add a vertical axis like this. And this vertical axis contains all imaginary numbers or multiples of pure I. So this would be I. This would be 2I. This would be 3I. Okay, and so this is useful because now if you ever want to think about what are all numbers that exist in the world, in mathematics, all numbers, just like, every possible number that exists. Well, what you can think about is the complex plane. The complex plane, this is the complex plane, contains all numbers that currently exist in mathematics, all of them. Absolutely every number that currently exists in mathematics is contained in the complex plane. Why? Because think about a complex number. If I want to get to 1 plus 3i, well, that's going to be, let's see, 1 plus 3i, that's going to be over here. Minus 2 minus I is going to be right here. I just located those two complex numbers. And so any of the infinite possible combinations that you can make here are represented in the complex plane. But even real numbers are contained in the complex plane, because that's just when you have the imaginary part is 0. That means that the coefficient b is equal to 0. So then you're just back on the real number line. You see? And so in that context, what's interesting to think about is how technically real numbers are complex numbers. They're complex numbers with the imaginary part being equal to 0. Okay. So now, two complex numbers, a plus bi and c plus di, are equal provided that their real parts are equal and their imaginary parts are equal. So what that's saying is that if you could think about this from the perspective of the complex plane, for two complex numbers to be equal, really for two real numbers to be equal, for any two numbers in the truest sense to be equal, they have to be at the exact same point on the in the complex plane. They have to be on top of one another. And the only way that's going to happen is if the real parts are equal and the imaginary coefficient is equal. If one of those aren't equal, then you're going to be somewhere else on the complex plane. And that's the meaning of the equality of complex numbers. That's what equality means in terms of complex numbers. Okay, now here they lay out some notation. This is the official or notation or wording for complex numbers, imaginary numbers. I know personally sometimes I'll say imaginary numbers or an imaginary number when I'm referring to a complex number. Like I'll call this an imaginary number sometimes, but the official math wording for this is that so if b is equal to 0, then what you're left with is a real number, right? Because you just have like this is a complex number with b is equal to 0. We call this a real number. But, again, that's technically still a complex number. That's what the number 2 is technically. This is a complex number. So, yeah, real numbers are a subset of complex numbers. That their real numbers are in the complex plane is what that's saying. Okay. Now, if you have b not equal to 0, so if you have just a standard, a standard complex number, 2 minus 5i, I think we typically just call this a complex number, but that the technical word would be that's a non-real complex number, in the sense that it's kind of like, this is the real part, this is the imaginary part. 2 plus 0i, this is just a real number or a real complex number, but this is a non-real complex number. Okay. Now, what if you have 0 plus 3i? So a is equal to 0. That's they call that a pure imaginary number. So that's the notation. Now, another point to note is that, the form a plus bi or a plus ib that's the standard form for a complex number. And they write it in two ways here because, we would do 5 minus 3i, but if we have something like a radical, you could do that, but sometimes it might be confusing that it could seem that the I is under the radical. So a lot of times you'll see people write that like this, and they're saying that's fine. Okay, so now to sum up all of the sets and subsets when it comes to complex numbers. So every number that exists in the universe that have been defined by humans currently in the year 2025 fall under the category of complex numbers. So real numbers are all complex numbers, and then there's all like rational numbers, integers, whole numbers, etc. Those are all complex numbers. But then there's also the non-real complex numbers. And then a subset of that would be the pure imaginary numbers, because every pure imaginary number is a non-real complex number with the a equal to 0. Okay, now, the next thing we want to talk about is what is the meaning of, the square root of negative a. So like it's not negative 1 anymore. A is any real number or any positive real number. So like the square root of negative 4. How do we interpret this in the context of the definition of I? But we're saying a is positive. If a was negative, it would just turn back into a regular root of a positive number. Okay? So what does this mean? What is what does the principal square root of a negative number that's not just 1 mean? And notice I'm saying square root, right? So this is, we're not talking about just even roots here. We'll discuss even roots later. Right now, we're strictly talking about the principal square root of a negative, any negative number, real number. Okay, well, you interpret this as you take out an I here, and then you put that multiplying the square root of that, the positive of that number. That's it. So if we look at these examples, the square root of negative 16 would be I principal square root of 16. So that would be 4I. And that's the answer. That's a complex number, right? A pure imaginary number. Okay, what about the square root of negative 70? Just take out an I, and so you have I times the principal root of 70. You can't simplify that anymore, so you're done. I root 70. You see here they put the I second, and here they put the I first. So however you want to do it. Okay, what about the principal root, square root of negative 48? Well, you do, let's see. You take out an I, and you put just positive principal root of 48. So let's see, 48 is 24 times 2. This is 12 times 2 times 2. 4 times 3 is 12. So 16 times 3 is equal to 48. So the square root of 48 is 4 root 3. So you've got 4I root 3. Like that. And there you go. Okay, now you might look at this and think, well, yeah, this is really intuitive, because if you think about, so if you have the principal root of minus 4, you could kind of look at it this way. And we know when it comes to radicals that you can, a property of radicals is like if you've got any radical, not just a square root, times, you could do this. So that's kind of what you're doing here. And yeah, I guess you could kind of think of it that way, but the only issue with this is that you can't, this would be completely incorrect to combine these this way. You can't do that. And we'll see why you're not allowed to do this in a second. This property here of radicals only applies once you have positives under the radicals. You're not allowed to combine them this way if you have negatives under the radicals. So thinking about the meaning of the square root of negative a this way, you want to be careful with. Okay, complex solutions of quadratic equations, part 1. Such solutions are expressed in the form a plus bi or a plus ib. Yeah, okay. So solve x squared is equal to minus 9. All right, well, we know from algebra to solve this, we take the principal root of both sides, principal square root, but then apply the square root property. So put the plus or minus. So we're left with, okay, now before this, we wouldn't know what to do here, but now we know. We take out an I, and then so we have, okay, and then what we're left with is plus or minus 3I. And that's the answer. We're done. Now, what about x squared plus 24 is equal to 0? Subtract 24 from both sides. Apply the square root property. So now take out an I. Okay, now 6 times 4 is 24. So you're going to have 2I root 6. Plus or minus 2I root 6. And there you go. Now, what about equations that require you to take radicals of both sides that involve even roots other than 2? Well, we're going to come back to that later. That can get a little more confusing, but we're going to come back to that later. Just note that these equations here were quadratic equations. They only involved these square roots. They're taking these principal square roots of both sides. This meaning here was only regarding a square root. That's it. So it's important to note that. Okay, operations on complex numbers. Products or quotients with negative radicands are simplified by first rewriting the square root of negative a as I root a. So I'm not sure why they're not explicitly mentioning that. We're just talking about square roots at the moment. So yeah, keep that in mind. We have not learned anything about, we're not making statements about like the fourth root or the sixth root of a negative number. Not yet. Okay, so what they're saying here is that in general, if you're dealing with an equation or any kind of math situation and you have a principal square root of a negative number, then you start the simplification process by taking out the I, and then you go from there. What they're trying to state here is that don't start doing operations with this like it's a regular real number in the context of everything we learned in algebra regarding radicals and whatnot. You're playing with fire if you do that. You want to, the first time you see this, go ahead and take out the I and turn it into the square root of a positive number. That's the first thing you want to do to simplify. At least if you're going to have this interacting with the rest of the equation or the math system you're dealing with. Okay. Then from there it says, then the properties of real numbers and the fact that I squared is equal to -1 are applied. Yeah. So once you get to here, now you can start operating with this with the rest of the math equation or whatever. And what is this? Well, you have I, that's the square root of, I squared is equal to -1, or the square root of -1 is equal to I. And this is just like the square root of a positive number, the principal square root of a positive number. And now you just go from there. And they're pointing this out because, okay, if we had -4, the principal root of square root of -4 times the principal square root of -9. Well, okay, again, the first thing you want to do is, if you want to start simplifying this, you take out that I in each of these. Then you can start doing operations. So we could multiply these. We'd say I squared times, and then 9 times 4 is 36. Okay, so principal root of 36 is 6. I squared is -1, so done. Okay, but if you don't do that, if you just start doing the standard math stuff that we learned, not in relation to imaginary or complex numbers, from this point, what happens? Well, we know this property. This applies for any radical, so let's apply that here. Well, no, that's wrong. That's wrong. And you can see the reason why is because we bypassed the whole utility of I, because we combined them and then we multiplied -1 by itself, and then that whole issue we allowed it to manifest itself with this. We didn't take advantage of the reason we invented I in the first place. So that's the idea when it comes to, and this is gonna extend to when we learn about just any even radical of a negative number, like the fourth root of -16. You wanna apply the I to it, whatever I is used for to simplify it first. So you can state explicitly, okay, like this involves the square root of a negative number, then start operating with it. You don't ever want to get something like this involved in an equation before you kind of identify the I that's associated with it. Okay? So they give some examples here, like here's a, so we know that same property applies with division. Okay, but you can't just do that before you take out the I first. Then you can do it. Okay, so we'll work a bunch of examples and you'll get the hang of this. Let's see, simplifying a quotient involving the square root of -a. So if you have something like this, put it into standard form. Well, okay, the first thing you want to do before you start operating with this, or having this square root of minus 128 interact with the rest of the expression, take out that I. So you put it into, you make square root of negative 128, 8I root 2, then you start combining it with everything else. So you can factor out a negative 4, just a 4, cancel the 4s, and then you're left with, you have a complex number. Okay, now, so with the definitions that I squared is equal to negative 1, and you can think about how this, if you say I squared, if you use the definition of I in the sense that I squared is equal to negative 1, then that's kind of an all-encompassing definition, because this is only based on the principal root, right? Return the positive. This is based on the principal root of negative 1. This is kind of all-encompassing. So, but it doesn't matter. I just want to point that out. So with this definition that I squared is equal to negative 1, and that the square root of negative a is equal to I, the principal square root of negative a is equal to I principal root of a, principal square root of a, all properties of real numbers are extended to complex numbers. Okay, so what we're going to do is, in the next video, we're going to look at how properties of real numbers like addition, subtraction, multiplication, division, etc., roots, we're going to extend those properties of real numbers to complex numbers, with the goal that we can fully operate with complex numbers mixed in with real numbers with no issue.